Hello, everybody. This is Professor Ma, and this is the section on related rates. One central concept in going through this section is the ideas of the change in distance. When we talk about rates, we can talk about changing distance as a rate. For instance, if I were to move elongate this line at a steady pace or non-steady pace, I can write the rate of change as d prime t or the distance change t. Or if I interpret this as length, it will be length dt. The same thing, for instance, with this triangle over here. If I were to reshape these right triangles in some size, and then the size A, B, C, the length will be different, and they will change according. So the dA dt will be the change in side A, length of A. Okay, and similarly, B prime of T will be changing the length of B, and C prime of T will be changing the length of C. So as they move, so we are dealing in these problem related rate problems of moving pictures, and we try to track different measurements as the picture progress. So in these talks or these sections, everything will be based on the given the variable, independent variable respect to t. Okay, so here's another example. Suppose I take in in PowerPoints, and here's a rectangle, and I'm going to, it has length and width, and I'm going to drag the rectangle elongate, and the length and width change as I drag it in terms of t and time as I drag it along, and the relationship in these pictures that doesn't change is the area is always the length and the width at that instance. So I have this law area equal to length times width, which is always true as the rectangle changes. Now, as I drag, the length and the width, the distance change. So if I tell you how fast those distances are changing, the length and the width, that is their derivatives. In turn, I can compute how fast this area of the rectangle is growing. So, uh, so these type of problems, when a variable is based on various other variables, and when various the other variable change, each one according to has its own rate uh, with respect to the variable t, then the question is how do they piece together to to give you the change of the variable of original independent variables. Okay, if that makes sense. Also. So in other words, okay, the area A depends on L and W, but it also depends on that the growth of the area depends on the L and the W, and the rate, the distance change in L and W, the rate of change in the length and width. Okay, so to do that, let's practice a little bit of algebra. So in here, the assumptions we have is everything is in functions of t. Very important. Okay. Therefore, if I were to take the derivative of this, I'll have to use product rule. And I don't know what the derivative of x with respect to t is. So x prime over here. By the way, the prime over here is d dt. Okay. So, and then I get dx prime plus dx dt. and y squared to be derivative taken with respect to t will be 2y dy dt. Okay, so these will be what's in prime notation, which we keep in mind in the back of our mind. The prime over here means d dt. And the next example actually have the d dt written explicitly. So these are two different notations. And first I will write it as the products and use the product rule. And then the front, I use the chain rule is 2u du dt. And the back is e to minus e times dv dt. And this is as far as I can. And of writing the derivative, expanding the derivative of these expressions in terms of the u and the v and the du dt dv dt. Okay, in the derivatives, this is as far as I can expand. So this algebra will encounter in these type of problems, expanding things in terms of dt. Okay, so let's go to the specific problems of the rectangle. Okay, suppose here's a rectangle problem. Okay, suppose now I tell you as we drag along the rectangle, the size, the change in the size that is, oops, excuse me, that is the rectangle is the size of a rectangle at an instant is 6 by 4, the length times width, and the length and the width. And the length is being dragged as 5 centimeters per second increasing, and the width is increasing at the rate of 7 centimeters per second. Then how fast is the area it covers being expanded? So in pictures, we have these rectangle, and right now it's, imagine it's 5 by, what was it size? 6 by 4, and it gets drag increasing at when at a size 6 by 4, the length and the width at that instance, the length and width is growing, expanding, and become bigger, and the length and the width, d LDT, dWdt, that are given. Okay, so I want to find out what is dAdt. So from the original measurements, which is always true, I can take the derivative with respect to dt on both sides, and that gives me, this is dAdt. Okay, if you want to use this is dl dt, and this is w plus l times dw dt. This is in the dt notation, but I'm using prime notations in this power in these examples. And then we have the rate of change in the length and width are given as 5 and 7, and the w and the l means at that instant how large is the rectangle, and it was 6 by 4. So you plug in this, the rates they are changing, and the size L and the length and width into then this equation, then you get the rate of change dAdt. Okay, and the units work out, because if this is 5 centimeters and this will be 4 centimeters per second, then multiply will be centimeters squared per second, the rate of change in the area. So the units work out. Okay, basically what's happening over here is this: as we drag the L prime is the rate of change. Okay, for instance, for 1 second it goes that much, and the length, the width goes downward that much. And what we have added is say, oh, the area change that is this much, all of these, it's roughly this and that. And that little corner is kind of the green piece kind of disregard. So this is a rough approximations. Okay, so this is how we calculate the rate of change in the area. Here is another problem, the distance measurements. Remember the distance measurement change as distance change, that means the speed, okay, rate of change in distance, or in this case, if the triangle, a triangle is changing, the shape of a triangle is stretched, like how I did in the beginnings. And then the sides, basically, the sides, each side will have a rate of change. That's dc, dt, dA, dt, dB, dt. But the cosine law says the A and the B and the C and the angles, capital C, these, they are always fixed. This is always true. The cosine law is the extension of Pythagorean theorem. The Pythagorean theorem is basically when capital C is 90 degree and this disappear, and I get the Pythagorean theorem. And if that's not 90 degree and it's off, then there's a little piece of adjustments and you need to for the A square plus B square. Okay. So this is a problem that we're going to use this law. Okay. So two cars comes toward intersection at 60-degree angle. Okay, so and they are traveling and each other's speeds given as 20 meters second, 30 meters seconds. And at a particular instant, car A is 30 meters, car B is 20 meters from the intersections. Okay, so here are the situations. Car B is going at 30 meters per second, and car A is here should be 20 meters per second going in that way. And there's an angle of 60 degree, and here's intersections. And okay, and the question is, what is the distance change? The distance between them change. Well, you have to given at what instance. Well, at the instant, go back to the problem, the distance change when A is 30 meters and B is 20 from the intersections. In other words, at the instance, B is 28, 30, I believe. Okay. So as first of all, the triangle, given this triangle by the cosine law, then the measurement d squared must follow these equations. And now I know how fast dx dt is. That's a rate at 20 meters per second. And I know the dy dt changes. That's a rate 30 meters per second. And they're negative because they're shrinking. They both are driving toward the intersections. So they're shrinking. So take the derivative both are respect to dt. Okay, x 30, y is 20, and the rate of change of x and the rate of change of y. Plug all these numbers into the right-hand side x, x, y after derivatives. There's a hunting derivatives here. Okay, we want to know the instance, how fast is that red line shrinking, d capital dt. So take the derivative with respect to t on both sides. And we have the x and y and the dx dt dy. These we all know from previous this list right here. Oops, flying x. Then there's on the other hand, there's a capital D over here. How do we get rid of that? Oh, that's that we have to go back, use the x and the y and plug in to find out what a capital D is. In other words, we can plug in x and y and figure out what capital D. Okay. And that's capital D. And now plug everything back into the equation. We can find d, d, dt. Okay. And this is what the numerical comes out. So at that instance, the distance shrinking at roughly 21 meters per second. So here's an interesting question. What's the closest distance they ever get? I don't want to hit each other. Okay, so leave that to you. Now, here is a problem. Again, it's a related rate problem that relates, again, geometry problem volumes and the expansions and the radius of the surface area. So we have a conic shaped water containers, and this is given the dimensions of the size of this cone, and they'll put waters in there, and we pour waters at this rate. This is something which you should realize. This means that the change in the volume, dV dt, the cubic, is a cubic meters. So therefore the volume is changing. So the water is being pumped into these conic shaped containers. So it's rising. And in particular, it's pumping at the rate, this rate, the volume being pumped into this rate. And what's the rate of the radius of surface area? That's what is x. Watch the surface not get expanding as the water being pumped into it. And what's the rate of the radius change as it grows? Okay, it seems like a lot of things, geometry over here to keep tracks of. Well, the basic problem here is you need to relate dV dt to this measurement x. So we need first how the volume's formula for the cone. Well, the volume formula for the cone is going to be 1/3 pi r squared h, 1/3 of the cylinder. Okay, and now the r is the x. Okay, now I want to convert h into x. So h, this is where the dimensions of the 3x5 comes in. It tells you how can we replace h in terms of the radius x. Okay, then this is usually how we deal with conic sections, cross sections, similar triangles. Okay. Now we're given dV dt is 2. That is v prime is equal to 2. Okay, so take the derivative with respect to both sides, respect to t. So this says dV dt and it's equal to 5 pi x squared over 3 dx dt. Notice, and in this case, I want to know what dx dt is. dV dt is the 2 meters being pumped into per seconds. So that's equal, dV dt is 2. Okay. And we have to plug in x. Once I find out x, I can solve for dV dt. Okay. So, and when v prime is 2 and x is 6/5, okay, and so that's one, I believe height equal to 2. Whatever the original condition, we can easily figure out x 5/5 and v prime is 2 meters per second, 2 cubic meters per second. Put into this formula, you can find out what dx dt is. Well, it comes out numerically roughly 0.265. Okay, so that's how all these different measurement change. In this problem in particular, and what governs this situation is the shape of the cone is confined to that dimension 3:5 ratios, and that we comes out with this volume formula. Okay, and that's these related ray problems. Okay, bye bye. Adios.